Work. And let me start recording. Always forgot about that. Sorry about that. So a quick repeat myself, just because I didn't record. The exam gonna be in 2 weeks, and we haven't decided on format yet. I'm meeting Dr. need to decide. For those of you watching online later, we're going to probably choose in person, but not sure how situation is, especially with the numbers of COVID cases increasing. But even if we choose in person, I believe we'll make all the possible measures to make it safe, especially social distance and the room and all the other environment. Okay, and but I have a strong feeling that it's gonna be in person, from my perspective, because we have seen a lot of issues doing this online homework, timing and problem and all that kind of stuff. But we'll keep you posted. Okay. All right. So that's about the exam. And again, you might be working on the slab, one way slab homework and share. Share is due already, and one way slab, give it a try. I'll see where we're at. I'm not gonna see if nobody has submitted. I will just give an extension. I'm not gonna do that. But instead, I will take a look at people who submitted and see where we're at and make a decision if we need extension or not. Okay. And we'll finish IG and the transformer section today. So we'll go ahead and release the homework for the serviceability deflection part just for this part. But as you're probably aware of, since we didn't cover much, so the homework is quite easy, okay? Quite easy. All right, so let's continue. A quick recall what we have learned so far, right? A recall the serviceability deflection, right? Serviceability, right? Serviceability deflection. Okay, so that is the topic we went over last time. Okay, and before we went there, right, we talked about several things. Especially we talk about materials modulus or modular ratio. We call it modular ratio. Okay, and that is dependent on the modulus ratio that is between steel and concrete. Between steel and concrete. And Austin, I just mute you a little bit, okay? There's some voice coming from you. You can always ask questions whenever if you need it, okay? All right, so the concrete modulus is pretty low. So roughly we have about 8 times of modular ratio. So it's safe to use 8, but it's case by case though when you do calculations. So when you don't know the concrete strength, use 8. When you know the concrete strength, you have to actually calculate it out. And mind you that EC equal to 57,000 square root of F prime C. Okay, so that is how you calculate the modulus of concrete, modulus of concrete. All right, so we talked about last lecture. Last lecture, we talked about moment versus curvature. So this is curvature phi, and we talk about moment here. And we mentioned that, let me just slide different colors, 3 stages, right? There's uncracked, cracked, elastic, and yielding. Uncracked, cracked, elastic, and yielding. Okay, so this is elastic, and this is cracked elastic, and this is yielding. Okay, so this is my yielding, and this is crack. All right, and we also talked about, we said stage 1 and 2. Stage 1 and 2 are mostly concerned for deflection, mostly concerned for deflection. Okay, mostly concerned for deflection. So we only need to calculate the moment of inertia for the transform section of the stage 1 and the cracked moment inertia for stage 2, right? So these are the moment of inertia we're trying to calculate here. Moment inertia we're trying to calculate here. Okay, so with that, let's take a look at what we talked about last time, right? So we said we have a section, okay, and this is, again, let me lower a little bit, lower a little bit more, and we say here is stage 1. This is for stage 1, and this is for uncracked, right? Nothing is cracked, right? It's uncracked. And then we have bars like this, and they have a depth of it, height of it, go this way, and width of it like here. Okay, since it is uncracked, so if I draw the stress or strain distribution in this way, stress distribution, right? So we know that it's a concrete compressive stress FCC. It's not failure yet. It's not failure yet. But we do know that at tensile end right here, FCT, okay, FCT, this is a tensile strength of concrete. So if you wonder where this stage is at, I can point right here. It's almost going to be cracking, but not yet. It's end of stage one. It's end of stage one. Okay. So you look at the cross section. Use black. You look at the cross section. This is the cross section, and we talk about it. We say, look, we have bars in it, and I'm going to convert steel. So convert steel into concrete. So convert steel into concrete. Convert steel into concrete, right? So once we done that, we replace the steel in terms of the little blue wings on the both sides and fill up the holes and return the rectangular section in the middle. Okay, fill up the rectangular section in the middle. Okay, and we also mentioned last time, right? There is a converted area of steel to concrete that is n minus 1 AS, n minus 1 AS. And the minus 1 coming from simply we fill the holes back in, okay? We'll fill them back in. Because when you take the bar out, you have those empty holes and we fill them back in, so you have to subtract it. You have to subtract it. All right, so this is what we're talking about. This is called the transformed section. So this is transformed section. Now, the moment inertia for this case is called IGT. 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 Okay, so in this case, we need to find out determine the centroid of this transform section. Determine the centroid of this transform. So if I assume this is the centroid of the transform section, so the height of the center of this transform section, the top is y top, y top. Okay, so how do we find out? How do we find out this center of this transform section? You learn it. You already learned it from mechanics of materials. You already learned it from mechanics of materials. But still, right? Still, let's take a look. Let's take a look. How do we do that, right? How do we do that? So let me just copy this section right here. Copy it right here. And then drag it down here so we can take a look. We can take a look. All right. So in this case now I can simplify a little bit more. Just want to simplify a little bit more. All right. I'm going to divide the section into two pieces. The filled in black piece, what I call it part one, and the blue piece, I call this part two. Okay, so first thing first, I need to find center of this section, right? I need to find center. So how do I do that, right? So I need to find y top in terms of equation equal to a1 y1 plus a2 y2 and divided by a1 plus a2. Okay, so give you some dimension. The area, sorry, the height of the beam is h. Okay, the depth is d. Okay, depth is d. So might as well use blue because this is only related steel. So this is d. Okay, so I want to determine my a1, right, which is the area of the fill in. So a1 simply equal to bh. Now the height of the black portion is basically the center of this dark area here to the top, which is h divided by 2. So this is h divided by 2. Right? That's easy, right? That's easy. Now let's take a look at A2. A2, we know the area. We know there is n minus 1 AS. Not bad, right? Not bad. Y2. What is Y2? Y2 is simply D. Okay, so that is the center of the transform the little blue wings to the distance, right? Distance between the center to the top. So it's YD, right? So then you can calculate your Y top. Calculate the Y top. Okay. Now to calculate the moment inertia IGT, okay, we need to have YI1 plus I2. 1 plus I2. Okay. So I1 is the moment inertia of area 1 with respect to the neutral axis. I2 is the moment share of these blue wings with respect to the neutral axis. Okay, so how do I do that? How do I do that? I have to use the parallel theorem. I have to use the parallel theorem. So let me just use a table to do that, right? Remember, use a table to do that. Okay, so how so, right? So let's take a look. Take a look. Okay, so first thing first, I need to find a area of one. Sorry, they're both to one. Okay, area of each one, right? Area of each one, right? So this is 1, this is 2. So for the first thing, for the filled in block, right? The area of this is BH. Simple as that, right? So BH. Okay. And the distance, let me call it D, but with a bar here. The distance, okay, this is the distance between centers. Okay, that is the distance between the center of each component to its neutral axis. Okay, so for the first thing, for the first area is h divided by 2 minus y top. Okay, and then I need to find its own moment of inertia. Own moment of inertia, that is 1 over 12 bh cube. 1 over 12 bh cube. Okay, now for the second piece, right, which is the little tiny wings here, the area n minus 1 as, that is straightforward. Distance between the center of this to the y top is d minus y top, right?
We can't see
So,
what you're writing.
oh, you cannot see it, sorry.
Nope.
Let me reshare my screen. Something wrong with my screen here. Can you see it now, guys? Is it back?
Yep, it's back.
Okay, good deal. Thanks. Sorry about that. So as you can see, I'm down to the distance between the second area, which is this little blue wings, to the neutral axis of the whole section, right? So that is d minus y top. D minus y top. Now, if I want to calculate the moment inertia of this whole blue area, I need to know the center of this new blue area, which is this one, right? And it's supposed to be 1 over 12 bh cubed, but the h for this area is so small. Okay, so I say because it's 1 over 12, some number multiply h, let's call it s to the cube, and this is very small. So I want to say this is approximately equal to 0. Okay, because it's too small. The height is too low, so it's approximately equal to 0. All right, so this is what I have. So using the parallel theorem, I need to find the total moment of inertia. Okay, total moment of inertia. Okay, so for the first piece, basically is a d, this is 1 squared plus I 1, right? Second piece, since I naught, the moment inertia with its own axis is 0, I only have n minus 1 ds, sorry, as, and multiply distance squared, so d minus y top, distance squared. Okay, so this is how we calculate the moment inertia for each component. Now the total, so IGT is this plus that, okay? So that is A1 d bar 1 plus I naught 1 plus n minus 1 as, and multiply d minus y top squared. Okay, so this is how you find moment of inertia for IGT. Okay, this is uncracked, and note here, this is uncracked, uncracked. Okay, uncracked. All right, and transformed, transformed, uncracked and transformed, uncracked and transformed. Okay, so this is for the elastic section, for the elastic section, uncracked elastic section. Okay, not difficult, right? You've seen this before, so I'm just gonna, you know, trying to rewrite it, trying to rewrite it. All right, so once you have these I transform, right? Once you have this IGT, if IGT is known after calculation, you can find determine the stresses. You can determine stresses. How, right? If given the moment, if given the moment, I can determine three stresses. Okay, what are three stresses? So compressive stress in concrete. So concrete compressive stress. Okay, that is FCC equal to moment multiply y top. Okay, because that's the location of the stress, and divided by GT. And the tensile stress, which is almost tensile strength, right? That depends on the moment, and H minus Y top divided by IGT. Okay, and note that this has to be smaller or equal to FR, which is the modulus of rupture. Okay, now this is, let me say, tensile stress in concrete. Now these are for concrete. Okay, for steel, it's a little bit different. Tensile stress in steel. Okay, for steel, it's a little bit different. Why? Because there's a modulus ratio. It's composite. You transform the section, remember? So for the steel, it is m multiply the distance, which is d minus y top. That's where the bars level, and divided by IGT. But don't forget to multiply a modulus ratio n. Okay, don't forget to multiply the modulus ratio n. And this modulus ratio n here equal to ES over EC. Okay, don't forget this, right? I'm sure you have covered this in mechanics materials, okay? Because I do that in my mechanics materials class, so you should have known that, okay? If you still feel strange to these equations, talk to me after class, okay? Talk to me after class. All right. So this is what we have. This is what we have for uncracked section. Okay, I got a question. Is IGT is a D1 supposed to be squared? I'm not sure what you mean, but when I calculate IGT, D1 is the distance of this shaded, black line shaded area, the center of this black line shaded area, which is half H, right? And to the center of this whole thing, which is Y top. So that is H minus Y top. You mean is it squared? Yes, right here. See this here? Because this area multiplied distance squared.
In the final box, whenever you like for where you say IGT is equal. Okay, yeah, there you go.
Thanks. Sorry about that, right? It's a typo. Yes, you're right. Thank you. Okay. Yes, it is squared. Let me check. Yeah, this is also squared. Thank you, Ben. Yeah, sorry about that. Okay. So it's squared. Okay. So it's squared. Good. Okay. So I'm sure you have seen this before, but like I said, if you still feel strange about it, let me know. We can talk about it. Okay. We can talk about. But this is that. This is for stage one. You have all the equations. You have all the equations. Okay. All the equation for stage one, uncracked, uncracked. Okay. What I'm interested today is to show you how to do stage two. How to do stage two. Okay. Stage two is cracked. Stage two is cracked. Okay, so what is stage two, right? What is cracked, right? So assume I have a stage two. I call it cracked elastic, elastic, right? And what do you mean by elastic? I mean the stress and strain relationship is still linear. It's still linear, right? To explain it clearly, so I have a section. I have a section, all right, and I have my bars, like I said in the previous case, and the depth is D, and all that, right? and have a width of b, of course. Don't forget that. Okay, and then when I get my string, it is linearly distributed. So this is epsilon c, which is from concrete, and this is epsilon s from steel. All right. Okay, now here comes the linear part. Here comes the linear part. That means if I label it in stress, right, I should see a similar triangle like in strain. Okay, I should see that. But unfortunately, it is cracked. It is cracked. Okay, unfortunately, it's cracked. So I have to remove this tension. I have to remove this tension because it's cracked. So after I've done that, the real stress distribution becomes, so this is stress. Let me see. This is FC. And the real stress distribution becomes just the top triangle. Okay. And the bottom, nothing but the steel. Okay. So if I have this case, right, FC is the concrete compressive stress at the top, and I assume my compressive zone C, you've seen this, and I assume it's KD, and K is just a factor. K is just a factor. Okay, this is assumed, this assumption assumed. Okay, now with this, right, I know immediately the centroid of the compression force is at a 1/3 of KD, distance away from top, that's the distance, and this is compression force, total compression force. Okay, and the distance between this total compression force to my tension is the lever arm JD. It's the lever arm JD. Okay, it's a lever arm JD. All right, so now with this, let's take a look at the transformed section, right? Let's take a look at the transformed section, see how the transform. So let me use back my black color. So here is my original section. Here's my original section. Beautiful rectangular, right? And we say it is cracked. So only the top in compression that still there for concrete, and the bottom just nothing. Okay, so essentially I only have this KD equal to y top. KD equal to y top. Okay, KD equal to y top. All right, now I still have bars at the bottom. I have these bars at the bottom, right? And remember what we said, transform means you convert steel into concrete. You convert steel into concrete. So what we're gonna do is we're gonna remove the bars, okay? And then replace it with a converted concrete strip at the same level of the bars, at the same level of the bars. And this is depth D. Okay, this is depth D. And now I know the area of this bar is supposed to be n minus 1 AS. But guess what? Since I don't have any concrete at the bottom, I don't have to fill them back in. So this is simply n multiplied by AS. N multiplied by AS. And the distance between this neutral axis now, this is a new neutral axis, and the center of this blue bar is D minus KD. D minus KD. Okay. All right. So the question now so far is that we assumed a compressive zone C equal to KD, and we just went down and show all the dimensions. But the real question is, what is KD? What is KD? What is KD? Right? What is KD? So what we're gonna do is we know that y top. Remember, if say this is 1, this is 2, equal to A1 D1 plus A2 D2 divided by A1 plus A2. And we know this is KD. Essentially, I can solve for KD. I can solve for KD. Right? How so? Let me just plug in the number. So KD equal to y top, right, equal to A1 area. So that area is, this is width B, and the distance is BKD, right? And the distance between the center of this block to the neutral axis is essentially just KD divided by 2. isn't it? And then plus the second part, which is the blue converted one, is NAS, and the distance is D, right? Distance is D to the, sorry, this is actually not to the neutral axis. Took that back, okay? This is the distance to the top. So for this one, it is all the way up to D. Yeah, so it's D, okay? Y top is, you see, Y top is taking the reference line at the top here, okay? This is the reference line when you're trying to find the centroid, okay? Sorry, made a mistake here, okay? So this is A1 multiplied by KD divided by 2 plus NAS multiplied by D divided by KD, okay, multiplied by B, this area, plus N times AS, okay? And now with this, I can manipulate it. Essentially, I can convert this equation, take this Y top variable out. I just have B KD squared divided by 2 minus NAS multiplied by D minus KD equal to 0. Okay, so I just have to solve for K, right? Solve for K, and I can get my KD, right? And to solve for this, I want to make it easier. I say, let's substitute, right? The reinforcement ratio, remember rho equal to AS divided by BD, okay? Divided by BD, and also N equal to ES over EC, okay? ES over EC, okay? And then after all this conversion, I can get K is a function of rho N plus rho N squared. And square root of this whole thing, there's a 2 in front of, okay? 2 rho N plus rho N squared minus rho N. Okay, and Y top, which is the center, equal to KD. Now this is a little bit long. You can try to derive it and learn it. If you don't have time, that's fine, but remember this equation, okay? At least put on your crib sheet for exam, okay? Put on the crib sheet exam, okay? All right, so once you know this, okay? Once you know this, you can simply use this to calculate the moment of inertia because you have the neutral axis. You have the neutral axis. Okay, you have the neutral axis. All right, so this is the procedure to calculate the centroid or the neutral axis for the eye cracked, Okay, all right, so this is as much theory as we want to go with this cracked elastic section. Okay, we will use an example in the next lecture, show you how we actually calculate them. Okay, so on Monday, you know how to do these calculations. Okay. All right, today's be a short lecture because I want you to guys have more time to work on the homework. And if you have more questions, even during the weekend, you can email me, okay? You can email me. So I'm just gonna stop here. It's gonna be a very short lecture today, unfortunately, just because I really feel like you want to slow down to work on your homework first, okay? And now let me stop recording and I'm ready for any question regarding homework or lecture so far, okay? All right, let me do that.